Hi, welcome back. This is the third piece of Unit 2. This is really going back to sections 2.1 and 2.2. We're talking about tangent lines and writing equations and all that other good stuff. So we're going to write the equation of a tangent line for a function at a point, find horizontal tangent lines from a derivative, and then graphs and derivatives. We'll get to that in a little bit. Your homework, your practice problems are on the right-hand side there from the textbook. Alright, so let's get started, I guess. Finding the equation of the tangent line of a function at a point. There are three kind of simple steps to do that. You probably or hopefully remember this from last year, so it shouldn't be that new, but again, a quick refresher. You want to find the equation for slope by taking the derivative, so I get y prime is equal to 4x to the third minus 6x at this point 1, 0. So I got to find the slope of the equation at the point 1, 0, so I got to plug in 1 into x there. So I get 4 times 1 to the third minus 6 times 1, which is 4 minus 6, which is negative 2. So this is my slope at the point 1, 0. Then I want to write it in an equation using point slope form. So remember, point slope is y minus y1 equals m times x minus x1. Y1 in this case is 0, so I don't really need to write anything there, equals the slope, which is negative 2, times x minus 1. So there is our equation. If you wanted to put the y minus 0, like, it's not wrong. It's just, it looks garbage, but it's not wrong. They won't count it wrong on the AP test either, but you can leave it that way if you like. Okay, let's go to this one here. Again, I want to find the derivative, so I get 3x squared plus 1. I want to find the slope at the point negative 1. So I got to plug it into each x. Well, there's no x over here, so I don't know why I did that. Equals 3 times negative 1 squared plus 1. So this is positive 1 times 3 plus 1 is 4. So there's our slope. So then I get y. This is a negative 2, so this is negative 1, negative 2. So when it goes into point slope, remember we flipped the sign. So it's y plus 2 equals 4 times x plus 1. Then hopefully I did that one right. I did. Fantastic. I didn't do this one right the first time. Example 1 there, so that's why I had to go back and redo it. Alright, so let's move on. Fantastic. Finding a horizontal tangent line. So to find the function has a horizontal tangent line, you take the derivative, like normal, like we've been doing, and you set the derivative equal to 0. Okay? So find the graph where it has a horizontal tangent line. We did this in the last video. We did it with sine, cosines, tangents, or not, actually no tangents, but some trigonometric functions. We're going to do a little bit more with trigonometric, but some other actual polynomial functions as well. So I take the derivative here. So this is 3 over 3 is 1, so this is just x squared minus 4. I want to set that equal to 0, and I want to see if I can solve it. So this is going to be x minus 2, x plus 2 equals 0. So x is equal to 2 and negative 2. So there is where my horizontal tangents are for that problem. I solved it. This one I want to take the derivative, so I get y prime equals, remember, the derivative of sine is cosine of x. Constant goes to 0. I want to find out where the cosine of x is equal to 0. Okay, well on my unit circle, the cosine of x is here and here. So x is equal to pi over 2 and 3 halves pi. And I can keep going. I can go 5 halves pi, which is just this rotation here, and then back there, that's 5 halves. And I can go one more, and I can get 7 halves, and so on and so forth. I can keep doing that, so I'm just going to put a dot, dot, dot. Okay? That'll work out there. For this one, I am going to get the derivative is equal to 6. And if I say that's equal to 0, well, that's not true, right? 6 cannot equal 0. So we know in this case there is no horizontal tangent line. Okay, that's pretty simple because I can't solve that equation. There's no variables in it, so pretty self-explanatory there. Differentiability and continuity. There is an alternate definition of a derivative using limits that is useful when investigating the relationship between the differentiability and continuity. Remember, the derivative of f at c is f prime of c is equal to this. So this is the slope, right? This is the slope of the secant line at that point. The existence of this limit requires that the one-sided limits are equal. Okay, so from the left and from the right, actually that's backwards for you. From the left and from the right, you got to go that way. I think that's right. I don't even know. This is flips. I don't even know here. So a graph with a sharp turn. We know that absolute value equations, absolute value functions here. Well, let's back up a little bit. So this here is really the limit as x approaches c from the left of the derivative. Okay, and we think, and that has to equal the derivative from the right. So that's just another way to look at this piece right here. Okay, and remember this was the slope. We have that down. We talked about that already. So now let's get into absolute value. We know that at the corner of an absolute value, there isn't the derivative does not exist. Right? It's continuous, but the derivative does not exist at that sharp corner, or turn, I guess, if you want to call it that. So if this is the function of the derivative, or of this absolute value, x minus 2, if I go from the left and from the right, since if they are the same, then we can have the derivative existing at that point, right? But because the derivative doesn't exist, these two limits from both the left and the right side need to be different. So if I calculate the actual derivative from the left, I can do that just by using the graph. That's just -1, right? So that's just -1 because I went down 2 and over 2, right? And then from the right side, I'm going over 2 and up 2, so that's just +1. Since they're not equal, we can conclude that the original function is not differentiable and it has no tangent line at x equals 2. So at x equals 2 right there, it is not differentiable. It's differentiable everywhere else on the graph into infinity, positive, negative, infinity, but at x equals 2, it is not differentiable. Even though the function, the absolute value of x minus 2, is continuous everywhere. So this is continuous everywhere. No matter what point you have, whatever, it's continuous everywhere, but it's not differentiable at x equals 2. That's the only difference between differentiability and continuity. Okay. The graph with a vertical tangent line. So if I have f of x equals x to the 1/3, this is really the cubed root of x. Okay, that's just another way we can write it. The cubed, x there. Oh man, that's terrible. Let's do that. So this is the cubed root of x. F of x is continuous at x equals 0, as obviously this is the graph of it. But because the limit, okay, at 0 is what? Well, the limit at 0 is x to the 1/3 minus 0 over x, which is then equal to the limit as x approaches 0 of x to the 1/3 over x, which is equal to the limit as x to the 0 of, now I can reduce this a little bit and I get 1 over x to the 2/3, okay, which is equal to 1 over 0, which is undefined. Which we can definitely tell me the derivative, this is the derivative formula, right? If I take the derivative and I just find the slope at 0, it's a vertical line, and vertical lines are undefined. So, well, because the limit's undefined, it's a vertical tangent line. That's what that means, okay? If I draw your tangent line and it becomes vertical, then we know we have an undefined slope, okay? That's pretty self-explanatory, hopefully. Differentiability implies continuity, but not the other way around. So, for instance, right, we talked about some other formulas, some other theorems and things like that, like IVT, right, is one intermediate value theorem. And we'll get into more of that, but and mean value theorem and all the other theorems that we've talked about. But differentiability implies continuity. So if a function is differentiable at this point, then we know it has to be continuous, but not the other way around. So if you said if it's continuous, then it's differentiable, well, that's not true, okay? Because this function here, right here, is continuous at x equals 0, but it's not differentiable at x equals 0. And the same thing with that absolute value graph of x minus 2. It's not differentiable at x equals 2, but it is continuous there. So this does not mean that if a function is continuous, it also is differentiable. Graphs with either a sharp turn, we call these a corner, right? Or potentially a cusp. Oops. Cusp. Oh my gosh, I can't write today. Corner, cusp. There we go. That's like something like that. Something that looks like that. Or a vertical tangent are not differentiable at that point where either of those actions occur. So in this case it was x equals 0 because that's where the vertical tangent happens, and the other one was x equals 2 because that's where the corner happened. Okay, we got to watch out for that, and I know you guys will. And so we're just, again, quick review. So that's this video in a nutshell. On to the next section. Deuces, my gooses.